Thanks for coming to today's CWS seminar. Also, people join us online. So today we have Peter von Lany from Jacob. He's the director of Jacob, who's responsible for the climate change adaptations, and he's been quite supportive to all our activities in giving several talks at our CWS seminar. That today is another one. Peter is going to share with us his recent work on the developing the adaptation pathways to manage the future flood risk and the water quality at regional scale.
Thank you very much, Albert, and thank you everyone who's taken time to attend, both in person and online. So what I'd like to do today is briefly reintroduce, some of you may have been here a year ago when I talked on a similar theme of adaptation pathways, so I'll reintroduce the concept, and then I'll look at a couple of case examples of where I've been involved in applying adaptation pathways in the flood and coastal erosion management context, and similarly where I've been involved in applying adaptation pathways in a water resources management context. And then maybe share a few ideas about the integration across both flood risk management and water resources management of the concept, because in the end I think a lot of us feel water systems need to be managed in an integrated way, and perhaps we can have a discussion about this. So basically, why do we need to adapt to climate change? And so a lot of my work is involved in infrastructure systems that have long working lives. And so one needs to consider the implications on performance of these systems due to changing climate. We know that climate projections are associated with deep uncertainties. These are irreducible uncertainties. And the impacts of climate change propagate through the interaction of systems, physical systems, engineered systems, human systems, ecological systems. And these interactions are dynamic, complex, and potentially unstable. The potential instability has been highlighted down the road by the Global Systems Institute when they talk of global tipping points. They are, in a sense, reminding us that some of these interactive dynamics can lead to potentially unstable situations. And it's not just the climate that's changing, it's social and economic systems that change, the environment changes, technology changes, and our application of innovation changes. So in terms of these, this is taken from UKCP 18. So there's the United Kingdom, and generally speaking, to the right of this line that goes down the United Kingdom, the future climates are going to be drier. To the left of that line, they're going to be wetter. Above this line, they're going to be generally colder, and below that line, they're going to be generally warmer. But it's not just the trend changes that are important. I think it's also the extreme events that ride on top of these trend changes. So I'm going to be considering 4 case examples. I'll be looking at flood risk management examples to do with the Thames Estuary and the River Severn region. A coastal erosion example located at Dawlish, which some of you may have visited, and then a water resources example located in East Anglia. So what are adaptation pathways? At the heart of adaptation pathways are decision trees, event trees, if you like, where you've got a series of existing measures and you need to decide, do we do measure A or measure B? dependent on which measure we take now, will be subsequent measures. And in principle, we can identify a series of pathways where each of the sequence of measures is a building block along that pathway. And at certain points, there are decisions that have to be taken. The measure that's been implemented is reaching the end of its useful life or its effectiveness, and a decision has to be taken as to how best to adapt further. And what we're looking for are coherent sequences of actions that maintain the performance of a system into the future. Ideally, we'd like the adaptation actions to be robust, and by robust, I mean they have the potential to perform well across a range of future scenarios. These are, some people talk about them as low regret actions. At each decision point, prior to each decision point, there will be various signals that indicate the need to take additional action. Maybe flood defences are being overtopped more frequently than people would like. Maybe there are opportunity thresholds that are approaching. I mean, one of the climate change opportunities, people talk a lot about climate change risks and floods and droughts, but here in the southwest, there's a big opportunity around warmer conditions favouring the growing of grapes and the planting of vineyards. So if you're going to embark on this opportunity, when is the best time to buy the land and start planting the vineyard? Is it now, or should you do it in 10 years' time? Or, I mean, that's an example of a sort of opportunity that's related to climate change, and the other opportunities around investment in tourism. So these decision points are related to risk thresholds or opportunity thresholds. And then the final point is that adaptation can range from autonomous and incremental actions. That is, we adjust gradually to changing conditions, or flood defences are incrementally raised. But with a lot of infrastructure, it's quite difficult to incrementally increase. If you think of a water distribution network, you can't incrementally increase the size of pipes. You can lay a second pipe or a third pipe. So the increments vary from system to system. But in some cases, adaptation will have to be transformational. And by that, I mean you will have to adapt systems to behave in a very different way. You may have to relocate critical assets that are at risk from sea level rise, for example. You may have to rethink the way you deliver services. The development of adaptation pathways is best done, in my experience, within an iterative adaptive planning process. And this is a process that many of you will be very familiar with, where you start off by setting the context of a problem, you identify the risks and opportunities, you look at options, build decision trees, and look at the options that might be available to respond to climate risks and opportunities. Then these options need to be evaluated, and on the basis of the options that look attractive, you build adaptation pathways, which are then implemented and then monitored and evaluated. And it's an iterative cycle with a number of feedback loops within it. And these feedback loops are very important because we're all learning how to apply this process of adaptive planning, and the insight gained from it can be implemented in the next iteration. And a classic example of this is in the water utilities sector, where the water utilities have been producing every 5 years an updated water resources management plan. They are they have implemented this adaptive planning process, and at the end of each iteration, they are wiser than they were at the outset. So the other important thing is that it needs to involve the stakeholders. So right at the center of this iterative loop are the various stakeholders. And the process provides a decision framework within which the adaptation pathways can be applied. And there are key decisions that need to be made about levels of risk and opportunity. There are key decisions around options and sequences of options, and decisions made around data that's monitored and evaluated, and how is that then interpreted to move forward within the adaptation cycle. There are different forms of adaptation pathways. The examples I'll be given probably fall mainly into the predict and act category, where the adaptation actions are triggered by specific targets needing to be met or thresholds avoided, such as a flood risk threshold. But there are emerging another family of adaptation pathways that are directed towards alternative long-term futures. So maybe the predict then act envisages a community will be protected against flooding in perpetuity. The imagine and plan pathway might say, well, at some stage in the future, maybe we cannot protect this community anymore, and we'll have to think of relocation as an alternative. And so the destination, the long-term destination, can vary from situation to situation. And what's becoming increasingly important is the recognition that you need another set of pathways that integrate the actions the enabling actions that organizations and stakeholders need to take. Because it's one thing to develop the adaptive strategy, but then it's difficult to implement it unless you have full stakeholder support of that strategy. You can raise funding for that strategy. You can monitor and evaluate and periodically review that strategy. So maybe a few insights now from the application of adaptation pathways in flood and coastal erosion management. So the Thames Estuary 2100 study was the first application of adaptation pathways to long-term flood risk management in the United Kingdom. And I was fortunate enough to be able to work on that study, and Hulcrow, Sir William Hulcrow and Partners, the company that is now part of Jacobs, carried out, along with hydraulics research, Wallingford, a large number of hydraulic analyses. So what we have here is, there's the City of London, and this little red line here is the Thames Barrier. And you can see that the River Thames Estuary, along the River Thames Estuary, are areas that are flood prone. These are areas with are prone to flooding with an average probability of 1 in 100 years or higher. And this was taken from the...
Sorry, that's 1 in 1,000 years.
1 in 1,000, sorry, 1 in 1,000. And this is taken from the Environment Agency flood maps. These flood maps assume that the defences are absent. So it's slightly confusing, because this is not residual flooding. But this just illustrates the potential magnitude of flood damage, and the fact that upstream of the flood barrier, the Thames Barrier, London is vulnerable to fluvial flooding. And, well, technically the tidal limit is at Teddington, which is somewhere here. So this region is both the combination of fluvial and estuarial. So the Thames Barrier was constructed with two purposes in mind. One is to hold back storm surges that could propagate up the Thames estuary, that are the drivers of flooding downstream of the barrier, but also to create space to absorb fluvial flooding. So the idea is you shut the barrier when the tide is low, when the river water levels in the River Thames are low, and you let that capacity be used by floodwater coming down the River Thames and its tributaries. So it's managing primarily coastal flooding phenomena, but helping manage fluvial floods as well. So the Thames Barrier is the key component in the flood defence system, but there are other components as well, and the adaptation pathways that were developed in the original Thames Estuary 2100 study, which was published in 2012, envisaged the downstream raising of flood embankments. And then you can either say, we will gradually raise the upstream embankments as well, and then as the sea levels rise, we will improve the Thames Barrier. That's one pathway. And then we use the barrier plus flood storage, which is the phenomenon I've just described. And then when the flood storage is no longer adequate, that's the fluvial flood storage, we raise the upstream defences further. And we gradually adapt the system towards a tidal barrier with locks that allows traffic. Or we could go straight to that destination and thereby avoid the raising of barriers upstream. The downstream barriers, the downstream tidal defences have to be raised anyway, and they then form part of alternative pathways. There is also the idea of a new tidal barrier replacing the existing tidal barrier. And so the green pathway envisages the new tidal barrier with upstream raising becoming the keystone of a future adapted flood system. So here are the various triggers: sea levels rising in too many barrier closures, a storm tide going over the top of the Thames Barrier, and it's a way of communicating diagrammatically the main driver, which is sea level rise, taking into account the need for fluvial flood storage. And this form of diagram has been used quite effectively with stakeholder consultations in order to help people envisage the different future adaptive changes that could take place. So this is a route map for a performance-led system, the performance criteria being the protection of London against flooding. The next example I want to touch on is to do with climate change in coastal communities. So this was work we carried out for the Committee on Climate Change in 2018 and 2019. And the particular concern was the impacts on coastal communities of sea level rise, extreme surges, more frequent storm events, flooding and coastal erosion. And the opportunity there in green is warmer weather increases the number of visitors to coastal areas. So that's an opportunity that the Southwest is very well adapted to providing. And the particular case study I'd like to look at is the railway line at Dawlish. I don't know, have any of you travelled along the main line from Exeter to Plymouth? Well, it's a really impressive piece of engineering. The railway line runs along the foot of these steep cliffs, and the embankment, for want of a better term, on which the railway line is located is designed to resist both storm events and provide resistance to coastal erosion. And it was, you often get these dramatic photographs of the line being affected by extreme events. And there is a concern now that there could literally be a tipping point. There could be a situation, an extreme storm that washes away the flood embankment, and the flood embankment provides protection to the community of Dawlish. There could be severe erosion, and there are also literal tipping points associated with cliff stability. So it's a very dynamic piece of coastline that is not just influenced by sea level rise and storm surges, but also heavy rainfall that can cause cliff instability. So there are multiple threats and thresholds. So there's an issue around an acceptable threshold of coastal erosion. There's a threshold related to the overtopping by waves of the flood embankment on which the railway line is located. And there's also a threshold of acceptable level of cliff instability. So the way we structured the analysis was to think in terms of situations approaching the threshold, and before that threshold is reached, before the tipping point is reached, some sort of decision needs to be taken on adaptation. So here we've got a situation of three different systems, if you like: the erosion system, a flood prevention system, and the cliff stability systems interacting at a specific location. And this was a very high-level study. Having identified these thresholds and triggers, we looked at a range of adaptation activities that would start off with maintaining and upgrading current sea defences, and coastal planners think in terms of epochs, of long time scales, and so one adaptation pathway is to continue this current work into and beyond the end of the century, whilst at the same time thinking about possible relocation of cliff top properties. Another idea is to realign the railway line, to move it further out from the foot of the cliff to be able to reduce the slope of the cliff. But then that reduces the area of beach and erosion protection. Another transformational idea is to move the railway line inland, or hold the line and accept a lower level of flood protection, or relocate the community. So the incremental adaptation fell into this category, but all the other, and I suppose that's a form of incremental adaptation, but the others were to do with transformational adaptation. And underpinning all this, we identified activities around public engagement, land use planning, and environmental management. So it very quickly, the interaction of the different systems very quickly increases the complexity of the analysis, and B, the number of stakeholders that are involved in it. This example is from an adaptation pathways pilot that I'm involved in for the River Severn region. It's funded by the Environment Agency, and the aim is to develop at a regional scale adaptation pathways. And here, I think the argument so far has been much more about incremental adaptation rather than transformational, and essentially a trade-off between enhancing storage in the catchment to reduce runoff and renaturalizing rivers where there's a possibility of increasing floodplain storage. And by reducing runoff in the catchment and increasing storage along the rivers, can you reduce the dependence on either demountable defences or permanent defences? And what role needs to be played by the flood-proofing of existing buildings and the building of new flood-resilient buildings? The Environment Agency is looking into this concept of resilient communities. So the community, in a sense, accepts part of the risk management. It is impossible to protect all communities from flooding for all return periods. So this is designed to explore a portfolio of options where you're trying to reduce the flood peak by works upstream of the location of interest. And at the site that is flooding, you look at defences. Now these, at this particular location, these are demountable defences, but they could also be permanent defences. And there is this trade-off between investment upstream and investment at the site. And it also raises the issue of flood-proofing existing buildings and future buildings. So the adaptation pathway has proved to be quite a useful tool for doing two things. One is encouraging people to think in terms of a long future. And secondly, to encourage people to think in terms of trade-offs. And I'll come to this further on in the talk, raises the need to have evaluation techniques that can resolve trade-offs, because it's one thing to identify the trade-off, it's a much more difficult problem to then say, right, here is an optimal solution, or a solution that satisfies us, that keeps most people happy in a mix of future flood interventions, flood risk management interventions. And also, I think as people look at the bigger picture, people begin to say, well, the nature-based solutions, that the catchment and along the river also have co-benefits around carbon sequestration and improved biodiversity, and that needs to be factored into the evaluation process. Water resources. So the particular case study is that of Anglian Water. So Anglian Water sits within WRE Water Resources East and supplies water to resource zones to the east of Cambridge and to the south of Cambridge and to the north of the Wash, the area of Lincolnshire. So it's looking at, as a water company, it's looking at a long-term strategy to deal with a potential water resources deficit that gets increasingly problematic under climate change. It also gets increasingly problematic if you set aside the required amount of water for the environment that the Environment Agency is encouraging water companies to do, because the eastern part of England is dry. I mean, some years less rain falls in London than it falls in Madrid, and people tend to think of, it always rains in Britain, but it doesn't always. It may rains. Think of that map I showed at the beginning. To the left of the line running down the centre of Britain, you get significantly more rainfall than to the right. And this will get worse under climate change. So what Anglian Water is looking at is building new storage sites, raw water storage reservoirs. You've got one in the Fens and there's another planned in Lincolnshire. It's looking at water reuse. It's looking at desalination, so they're looking at desalination sites along the coastline. There's the Lincolnshire Reservoir, the Fens Reservoir. It's looking at backwash recovery. And this question mark here, subject to WINEP investigations, the WINEP is to do with these environmental sustainability targets. So if the targets are particularly severe, the water transfer schemes that are already being assessed may have to be augmented. And here are their asset management plans with a planning horizon of 25 years. So they are taking a medium to long-term view of the need not only to manage against the impacts of climate change, but also demographic change and the demand, the effect that this has on demand. So in the water resources planning problem, many of you may be familiar with this sort of diagram that water utilities like to use, and it underpins their water resources plan, where they plot the potential availability of water, that's the blue line, and here you've got potential availability of water, the water available for use potentially being reduced through the effects of climate change, the sustainability reductions, these are the environmental hands-off flow reductions, an additional allowance for drought resilience, and where the water available for use, the blue line, intersects the green line, that indicates the need to augment supply, reduce demand, or do a mixture of the two. The green line is underpinned by the red line is the distribution impact input, so that is the demand, projected demand into the future, and on top of that demand, water companies like to place an allowance called a headroom allowance, and this is an allowance for uncertainties in both assessing the demand and the availability of supply. So it's a risk buffer. So what a prudent water resources planner will say is when the projected water available for use intersects the distribution impact plus target headroom, we're now in a zone where there could be restrictions to supply or interruptions to supply. So we need to do something. And so the doing something can involve a number of, I've shown on this diagram, investments to augment supply. This can be drawn as a decision tree. So the purple and blue lines are essentially supply side interventions, the red lines are demand side interventions, reducing leakage and demand management. And the sequence, in principle, you can have a number of different sequences of interventions, and in practice, these interventions tend to be implemented more as a portfolio, not as a strict set of alternatives. The decision tree can then be redrawn as an adaptation pathway where each of these circles indicates a possible switch to another pathway. So when the capacity of the drought, in this case imported water, when you've reached the capacity of the imported water, you've got to make a decision about augmenting the supply. Or when you've demand tends to be more incremental rather than have step changes in it. So it's a way, again, of looking at different sorts of measures, importing water, developing new supplies, managing demand, and relies on projections that are themselves subject to a range of different scenarios around climate, greenhouse gas emissions and climate impacts. Scenarios around growth will affect the demand and the location of demand. So in the Anglian Water Adaptation Pathway Water Resources Management Plan, they have identified a range of pathways which major on the elements of their core pathways are about upgrading water treatment works, increasing abstraction from surface water, groundwater, and building these two reservoirs, one in the Fens and one in Lincolnshire, and then exploring water reuse. The problem is in identifying the start date and the date in the adaptive plan, because of the uncertainty of future demand and climate change, you need to bring flexibility into the program. So the pathway identifies the potential need to bring forward desalination if the supply side measures are in some way delayed, and also if there's a need to significantly increase augmentation on the supply side to reduce the abstraction for rivers to retain their environmental characteristics. And that, I think, is the single biggest unknown. If you go to the Anglian Water Resources Plan, I think what keeps the planners awake at night is not so much climate change and demographic change, but the potential need to significantly reduce abstractions from rivers to maintain the quality of the riverine environment. So it's a more difficult set of pathways to explain to a lay audience, but I've just abstracted one image from a report to understand the pathway and the various parameters, the flexibility within it. You have to read the narrative in their report, but I think it captures an important issue of adaptation, and that is to try and identify where you have flexibility, because there are three sorts of flexibility. And given that the uncertainty is irreducible, how do you deal with uncertainty that's irreducible? Flexibility. So you've got flexibility in the size of options, you've got flexibility in the sequence with which you implement options, and you've got flexibility within the expectations that you set around performance. And adaptation, I think, needs to bring together these three areas of flexibility and use them in a way that is commercially efficient if you're a private company, and socially equitable and sustainable. At the end of the day, the main reason for embarking on adaptation is to underpin sustainability. So my proposition is that the processes I've described very rapidly are generic. And here's some work that was published by Marion Hasnoot and colleagues from the Netherlands, and I think sets it out quite nicely. You're looking at scenarios about the future. You've got models at the center of this. You've got models that help you simulate systems. You're looking for conditions that signal the need to adapt. So typically projected performance and some sort of threshold. So, are we crossing those thresholds or likely to cross those thresholds too frequently into the future? You've got condition assessments around probabilistic information. So, typically in flood risk management, you've got conditions around the drivers of flooding, peak flood flows, you've got information around the physical condition of assets, and you can create combined probability plots that explore the likelihood of flooding either through overtopping or asset failure. And as I mentioned right at the beginning, it's a very participatory process. Not only bringing together different disciplines, but also stakeholders. And the idea of storylines becomes quite important in dealing with stakeholders who maybe lay in their knowledge of hydraulics or water resources planning. And the idea is to produce a set of adaptation pathways that bring together these ideas on adaptation actions and embody flexibility. So alternative pathways, as the future unfolds, you can move from one pathway to another. So it's setting out a set of route maps into the future. And my feeling is, given that it's generic, the time is now right to bring together, and this is where the academic community, I think, comes in, because these are, how do you integrate two slightly different but broadly similar processes? So the time is right, because DEFRA and the Environment Agency, under their innovation program 2022 to 2027, is exploring and testing this idea of resilient communities developed through adaptation to climate change. And three of the projects that I've been involved in within this program are the Thames Estuary 2100, which I talked a bit about, the Humber Estuary 2100 project, which is exploring ideas around communicating adaptation and flood risk management to stakeholder groups. So they've done a lot of work on how do we represent and evaluate different pathways and use them in stakeholder consultation and discussion. And then the River Severn partnership, where we've looked at developing a set of pathways across the River Severn region and its tributaries, initially focusing on flood risk management adaptation, but ready to broaden this analysis to incorporate water resources issues. And the water resources issues on the River Severn, there are two very important ones. One is the River Severn is regulated by flood releases from Clywedog Dam, but in periods of dry summer flow, water is abstracted from groundwater, the Shropshire groundwater scheme, and pumped into the River Severn. So you've got augmentation of low flows by abstraction from groundwater. So there is a link, isn't there, between groundwater replenishment and, you can envisage more flooding of the floodplain in the along the River Severn in the Shropshire area, helping replenish the aquifer. The other issue around the River Severn is the long-standing idea of potentially transferring water from the River Severn to the River Thames, and this has been talked about for the last 50 years, and it's gradually gaining momentum because as the southeast becomes more densely populated and potentially drier in the future, there is this idea that you could augment flows in the River Severn catchment from flows, in the River Thames catchment by taking flows from the River Severn catchment. There are, however, concerns about ecology, the transfer of ecological cross-contamination in its very broad sense. Because the other interesting point around the integration of water resources and flood risk management is the idea of water quality, and that is the Cinderella. People are beginning to realize now that through the catchment management you can possibly reduce agricultural runoff, which will improve your water quality. So that is another issue that needs to be brought into the analysis. On the water resources side, you've got Ofwat's long-term delivery strategy, which has been exercised in PR24, Performance Review 2024. And so Ofwat, as many of you will know, set a requirement that water companies plan their water resources and their asset management with a look-ahead period of 25 years. And these are reviewed every 5 years. This is what I meant by an adaptive planning process that is working well. And under the long-term delivery strategy, Ofwat is asking water companies to set out a core pathway and then alternative pathways. And these alternative pathways will respond to changes in these scenarios. So here are the scenarios that water companies are required to consider in their planning. You've got two climate change scenarios, a high and a lower representative concentration pathway. Changes in technology scenario, demand scenarios, and then abstraction reduction. And the abstraction reduction is the one I think that is the most significant area of uncertainty, because it has to take into account the potential restrictions on abstraction for environmental reasons. But the thinking is the same. You've got decision points, trigger points. So my feeling is the time is right to bring together the activities in these two domains. And in the Environment Agency and possibly DEFRA as well, I think the people that are still working in relative silos, you've got the people that understand flood risk management, people that understand water resources planning, and I think the time is right to integrate thinking on this. And maybe academic institutions have a role to play in this, in developing approaches that build on, it's a sort of a generic toolkit, if you like, to help organizations to extend the application of their adaptation pathways. So there's quite a lot already out there. There are international standards on climate change adaptation. There's a British standard on applying adaptation pathways. The climate change risk assessment, we're now gathering evidence for CCRA4. That is refreshed every 5 years, setting out climate risks and opportunities. The Committee on Climate Change progress reports to Parliament on mitigation and adaptation, actually always draw attention to they're slightly disappointed with the lack of scale and ambition in implementing adaptation in the UK. And there are reasons for that, which we can perhaps discuss later, because I'm running out of time, but I wanted to leave a little bit of time for discussion. And other utilities are embracing the idea of adaptation pathways. Network Rail has published an adaptation report. And then the umbrella around all this is the periodic, every 5 years, the DEFRA produces a national adaptation program, which tries to look across adaptation in different sectors. So in really to sum up, I think regional water resources planning groups are looking beyond just water resources management to managing water systems as a whole. So aquifer recharge is a good example of that. The Environment Agency and climate change partnerships recognise the interconnectedness between water resources management, flood risk management, and the role of water quality, ensuring environmental sustainability and water quality. So effective adaptation, the idea is gaining momentum, and it's recognised that it's essential to sustainability. The challenges lie around integrating different disciplines. I've said a little bit about that. But the other big challenge is business case development and adaptation funding. I think the problem with adaptation, if you consider it alongside mitigation as a response to climate change, is that with mitigation, you've got clear targets. You could say, these are my carbon emissions today. That is what I would like to reduce them to in 10, 15, 20 years' time. And you can identify a trajectory. What is much more difficult is to measure adaptation, because a lot of adaptation is about building flexibility into a system in the short to medium term. But the benefits won't accrue until the much longer term, because it's this flexibility that will reduce the exposure to long-term climatic damages. But it's very difficult to put that into a business case that attracts private investment, because private investment likes things to be a bit more tangible. Though in terms of the government and the progress towards resilient communities, there's a certain sense that I was at a conference 10 days ago, and Emma Howard-Boyd, who was previously head of the Environment Agency, said adaptation is non-negotiable. If you look at the macroeconomic arguments for adaptation, you would be foolish not to adapt. But it's trying to build this into the business case. And then the opportunities. Well, these are opportunities you might be interested in. The integration of systems analysis and simulation modeling to identify the different hazard pathways that can be triggered by a changing climate. And not only a changing climate, improved technology, because it's essential to have a set of tools which enable you to explore different options in order to be able to build these pathways of proposed options for the future. They involve integrating risk assessment techniques, stochastic simulation, with multi-criteria analysis, because a lot of the pathways have multiple attributes that can be compared most effectively with a stakeholder group through multi-criteria analysis. But more advanced approaches are being trialed, and they look at applying scenario analysis to explore ideas of robustness and regret. So what adaptation actions are most robust against a range of futures, And what would we least regret investing in if we may have to make these investment decisions in the face of uncertainty? And then the role of optimization to support robust decision making. And I think there are people gathering at the door, so I don't see any questions from the online audience. Are there a couple of quick questions in the room? Yeah.
May I?
Yeah.
So, Peter, first of all, thank you very much. This was very insightful. Well, just looking at your last slide regarding assessment of adaptation pathways and funding. So each pathway comes with a set of measures to be taken at a certain time, and then those can be associated with flood events of different probability for each assumed pathway that come from climate change and urbanization predictions. So for each of those combinations, we can assess expected annual damage, and then we can look at that in the context of how much it costs to do this or that. And then we can present those things to stakeholders. So we've been doing that for years in the UK and around the world. So is that not, how do you say, if I can ask you a specific question, of the three, your first three cases you talked about, London, Dawlish and Severn, so which one went furthest in the highest level of detail into effectively assessing different types of damage and presenting?
I think the Thames Estuary one, because I think the concept of expected damages and damage avoided is quite well embedded within flood risk management. Within water resources planning, water utilities tend to minimise costs rather than avoid expected damage. So the idea of expected damages is less well embedded within the analysis. But the big problem with expected damages is expected damages under which future scenario? And I think it's the uncertainty attached to climate change. So do we work out our expected damages assuming the current trajectory of climate greenhouse gas emissions? Or do we stress test it against alternative trajectories? And once we look at alternatives, we have to assign a probability. And that is problematic. It's very difficult. The papers I've come across assign equal probability to all three scenarios. Typically they use a mid-range climate projection, high and a low projection. And I think that is